Recording have been started. So let me guide you where you can find those materials, the one we are using for today. I have them in module, and this is the module course. So for week, for week 4, this is the current week, you'll find that there is a folder called Lab Session Earthquake Seismology. If you access that folder, you will find that there are 3 files. One of them is just a guidance. That's the thing I will talk about. Then there are 2 parts, lab 1, that's also lab 1, but part 2. We'll go through them one by one. But in general, you'll be doing 2 things. In earthquake seismology, we are interested in many things actually, but primarily we are interested where exactly the earthquakes has happened. What's the location of the earthquake? So I repeat myself, I'm seeing some people are just joining. So what I said that today is the first lab. This is week 4. However, from today or this week onward, we'll have a lab in each week. Unfortunately, they thought that we'll be back to the university and the study gonna be on campus. They made the lab 2 sections because the labs or the laboratories in our departments, they cannot accommodate 60 students. In each section, I supposed to have only 30 students, but things changed. We are still in online teaching, and I believe for online teaching, having only 1 section for the lab is sufficient. Whereas for the on campus, because sometimes you'll be working with computers, you'll find that from next week onward, sometimes your lab requires the use of a computer. You must have an access to internet sometimes too. Uh, so that's the reason actually why we split it into 2 labs. In geophysics, we used quite often computers. We do programming, but not in this course, in other courses, or we use ready-made softwares. So the material for today's lab are actually available in module. If you go back to the module, you'll find in week 4, there are a lot of materials existing for the week 4, but the one we are interested in are in a folder named lab session. If you access this folder, you'll find that there are 3 files. The one you're gonna submit to me are these 2, first, second. And there is a PowerPoint slide file. This is actually the thing I explained today.
Doctor, where is the slide?
The slides are actually a module. There you come.
No, for presenting today.
Yes. You should stay in quiet room or try to use some noise filtering app, similar to the way I'm doing. So in my case, I'm using this app. Oh, sorry. Yeah, I got it. Yes. Sorry about that. I get confused sometimes. Here are the slides, or actually what I'm presenting. Where you can find the material, you find them in week 4 and the lab session. Here you'll find the material you need to submit for today. The submission is by the end of this week. and how you submit something using module. Usually I make a link. So for the link for today is this thing, lab 1 earthquake seismology, and let me change it. Sub name it submission. You go there and you can actually upload. So I'm not sure, can I change my rule? Switch to student. That's what you're gonna see, and you add a submission. You can add as much files as you like. So the files, uh, please convert them first to PDF format. So you need to convert them. It's easy to convert them Word file, Microsoft Word files to PDF formats. And you can upload two files. You need to upload two files. Why two files? Because you will see that today. If you go back to lab session, earthquake seismology, you'll find there are two Word documents, lab 1 part 1 and lab 1 part 2. Apart from that, there is Microsoft PowerPoint slides. Those are the things I'm explaining. So this is some general knowledge I would like to give to you before we proceed with the lab. Whenever there is an earthquake, we are interested on some factors, informations about the earthquake. The most and foremost important is what do you need to know about an earthquake? If there is an earthquake, what you are interested on? What's the information? Location, simply location. Yes, I need to understand where the earthquake happened, exactly in which part of the earth, at least the epicenter. Epicenter is the location of the earth on the surface. Focus or hypocenter is its location down the earth. But we are interested on the location or the projection of the earthquake on the surface. And that's what we are going to be doing today. The scientists, seismologists, they care actually the location down the surface. So they can characterize the earth. They know where exactly the earthquake is happening. And why earthquake happens? Earthquake happens whenever the rock cannot withstand the stress regime. There is a stress whenever there are two plates moving side each other. Is either in transform way, the way you are seeing it in here, or convergent way, moving apart, or they are colliding to each other. For example, Arabian plate where Oman resides is moving toward Euro-Asian plate or Iranian plate, they name it too, along a subduction zone. That subduction zone is called Makran Trench or Iranian Trench, and it's actually responsible for the Zagros Mountains we see in Iran. The movement rate is about 1 to 2 centimeter per year. So if you got the chance to live for thousands or millions of years, one time there is no sea, there is no Gulf Sea between separating Oman from Iran, or Oman, Gulf of Oman, basically, or even Arabian Gulf, because Arabian plate is moving toward the Euro-Asian plate. And whenever there is a movement of big plates, as we know, there is a stress. Let me see. There is a stress, and stress accommodates strain. And at some point, the rock cannot stand more strain. Similar to having a pen, and you start bending it. At one point, the pen will break. There is a fracture in the rock, or there is a fault, a big fault, a rupture, a displacement. This displacement is supposed to be happening in very short time span, in the span of like seconds, 10, 20 seconds. The energy which is released by this rupture is tremendous. It's really huge. It expands and travels in every direction. And this is how the earthquake actually happens. So how I can record or know where it happened? We need some instruments. We need recording instruments. Usually we need more than one to record it precisely, to know where exactly the location is. One is enough. One itself is enough, but there is some ambiguity. I tell you how we can use one instrument, but this is not very important. Uh, I will not ask you any questions about how we record or know the earthquake location using one instrument. So for one instrument, we need three sensors. If you are having one instrument, you need to have three sensors to locate the earthquake. Another thing I would, it's not related to the slide, I will never include a question in the quizzes or exams related to the labs. You will be evaluated on the lab part based on your submission, report submission, the thing you submit by the end of each lab. So for one station, there's supposed to be three sensors orthogonal to each other. Whenever I say orthogonal, they are perpendicular to each other. And we analyze all three sensors. Analyzing the three sensors can tell us from where, from which direction the energy came to me. That how it helps. If you have one sensor only, you cannot tell the direction of wave arrival, from where the wave arrived, from which direction. And how I can tell the distance. If I know the direction, if I know, from example, some car came toward me or some guy came toward me from another point, I need two information. I need the time and the speed. First of all, I need the time and the speed. Time and the speed, they give you what? They give you the distance. And I need the orientation. Oh, then I can tell from which direction the wave arrived. I can tell you the wave arrival direction. And also I can tell then how far away the earthquake happened from me, because I already calculated the time of arrival, and I need to have a velocity model. I need to have some velocity model. This is quite complex because I need three sensors to tell me the direction of arrival or the orientation or the azimuth. However, if I don't have three sensors, I need three different stations, not in one place, in three different places. So in this case, I'm having three different stations, A, B, C. Each one recorded a seismogram. This is a seismogram. The seismogram, or the thing you are seeing in here, these traces and the shaking within those traces are related to some earthquake happened somewhere. Let me ask some guy a question. Asad, Hatmi, can you hear me, Asad?
Yes, yes, doctor.
Okay, I have three traces, A, B, C. All of them, they are recording the same earthquake. There is an earthquake somewhere, and it released some energy. The energy is those change in amplitude. And this is time. The x-axis is the time in minute, from 0 up to whatever. If I ask you which of these station is closest to the earthquake location, A, B, or C?
A.
Yeah, that's true. Why A? Because it took least time for the energy to arrive A. So earthquake happened at 0 time. It took how much least time compared to B and C? So this is closest to the earthquake than B and C. So if I have the time, I have also, I make a model of velocity of the earth. I can draw circles. And each one gives me a distance. Since I have velocity and time, each one gives me a distance. I draw a circle. So let me try to draw some circle. This pencil for A, it showed me that it could be somewhere here. Sorry, my drawing is bad, but this is the distance. For B, that's the one. Could be anything around this circle. For C, that's the one. So I can then guess the earthquake happened somewhere here. This is the epicenter. Differentiate between epicenter and hypocenter. Hypocenter or focus is the location of the earthquake beneath the surface. If you have only two, so this is one, this is two. How many possible locations are there? You have two stations.
2.
Yes, 1, 2. If you have another one, 3, it might come somewhere here. So the earthquake can be somewhere here. So for today, we'll try to guess where the earthquake happened. That's one of the labs. We'll use such a table. So we will use such a graph. I think petroleum engineers are quite familiar with these kind of graphs because they use it a lot in well logging or formation evaluation. They simplify actually the math. And they make these graphs based on velocity models. Instead of using equations, you use graphs. Like many other graphs determining, for example, in formation evaluation, determining, for example, from porosity logs, you can determine, is it sandstone, limestone? You don't care if you don't know what I'm saying, but petroleum engineers, they use quite often graphs to determine reservoir properties. Here we are using also some graphs. So this is one of the graphs which is very important. So instead we use just P wave. If you use P wave, you need also to know something else. You need to know something else, which is at what time the earthquake happened. Is it happened 5 o'clock, 6 o'clock? You never know. If you are recording only P wave. So we record something else. We record the S wave as well. Which arrives first? Anwar. How are you, Anwar? I think you are a petroleum engineer. Yes, sorry about yesterday. I was confused with a male or female, Anwar or Anwar. What was my question? I was having a question in my mind. Put it. Okay, what was the question? I tried to get another question. Anyway, sorry about that. I forgot the question. So I was explaining that there is a P wave and S wave. Oh, the question was actually which one arrives first, P and S wave? What do you think, Anwar? P wave, that's true. So whenever you write P wave, write it this way. P wave. It's one word. Or S wave. S dash wave or P dash wave. This is very important, especially for geophysics. So P wave arrives first, but we need to record two waves to eliminate or to know when exactly was the origin time. Why is that? Because at what time exactly the P wave and S wave were the same for a specific earthquake? If there is an earthquake, at what time exactly P wave and S wave have the same arrival time? They arrive at the same time. What's the time? Who can tell me? This is quite a smart question. I think smart guys can answer this one. So Shamsa, she's. Are you following along with me for Shamsa? Maybe she's, or maybe the question is quite difficult. Yeah, Shamsa, when you think P and S wave arrive at the exactly same time, there is no difference between P and S. What is that time? Zero. It's zero time. Both of them they arrive at the same time. When you know that there is no variation difference in time between P and S, if you are just on the epicenter. If you are on the epicenter itself, location of the epicenter, there is no variation between P and S there. So that's the reason I need to record both of them to make some projection. Later on, we'll make some projection to know the origin time. So I need to know at what time an earthquake happened, because usually earthquake is a kind of energy I don't have control on. It's different than, for example, what we do in refraction seismology, where we hit the ground with a hammer or use a vibroseism. So the time is zero time. At zero time, we know that the P and S wave arrived at the same time. How is that? So this is distance in kilometer, and this is the time difference. The farther away I am from the origin or from the location of the earthquake, this is the location of the earthquake, the distance from the earthquake, the higher the separation between P and S. What's the separation between P and S exactly at the location of the earthquake is zero. So I use the difference in time between P and S instead of using only P. So this is for earthquake location, and discard. And for this one, you need to solve for lab 1 part 1. So this is lab 1 part 1. So if I go right away to the questions, this is the questions. The first question, examine the 4 seismograms above. Those are the 4 seismograms. One, this is first. Sorry, 1, 2, 3, 4. San Andreas. This is San Andreas. That's the Stanford. Lick Observatory, and finally Berkeley. They're all located in USA. So how I record the origin time of if there is, can I?
دكتور هنا كيف صعب هنا كيف نفرق بين الدي ويفز والاس ويفز؟
Yeah, I'm coming to that. Here, how you can differentiate? It's not easy. Yeah, it's not easy. You are having 4 seismograms. 1, 2, 3, 4. So before I ask question, before we go to the question asked by someone right now, who was asking the question? Abdulaziz, are you asking? Huh? Okay. We'll come back to that. But first of all, which one you think is closest to the epicenter? Which of these observatories? Or observatory is actually a place which contain a station, a seismometer, which records earthquake. Yeah, the third one. Ahmed, Blushi, Abdulaziz. The third one is Lick Observatory because it's taking least time, arriving earlier than the rest. And at what time it happened? How I record the time. So this is how you record the time. I will do it for one, you will do it for the rest. So this is the time, 20:33 minutes. That's the first one is hour, the second one is minute, and this is seconds. So at this line, it becomes how much? The red line, it becomes how much? 33 minutes and 3 seconds, 6 seconds, up to 45 seconds. Up to 45. This is 40. It continues from here to here, this line, the black one. You see my mouse? So what is this one?
Yes.
What is this one? 45 plus 3, 48, 51, 54, and so on. But this is where the P happening. This is where the P happening. That's the location of the P. So it happens at time what? 36 minutes. I go 36 minutes and how much seconds? I go in the red line 46 minutes and 45 seconds. That's the end. But I continue from here to here. 36 seconds and 48 at this point. Exactly. 48 seconds. 51 seconds. At this line, this black is how much? 51 plus 3, 44. But it's less than 44. 36 seconds plus how much? Let's say 43. Oh, sorry, 53. And so on. Shall I repeat? Shall I repeat?
Yes.
So we repeat it for another one. I repeat it for another one. So those are the lines. These are the lines. These are the recording line. This is the time. I keep always recording because I don't know when exactly an earthquake will happen. My station is always on. It's waiting for any shakings to happen. And this is a time stamp. That's a timeline. At this start of this time, here exactly where the mouse is, this is 20:33 minutes. And each line is 3 seconds. 3 seconds. And if I add them one by one, the last line here, if the break was here, so if let me do some snipping because I'm not sure how to. So if the shaking started here, let me change the color, make it the black color, black. So if it started here instead of here, the P wave would have been 20, 33, and how much? Yes, 6 seconds.
6 seconds.
6 seconds. 06. 06. But
Why,
it's not
Doctor?
happening.
How 6?
Yes. Huh?
How it is
6.
6?
How it's 6? Because this here is 3 seconds.
Yes.
This is 6 seconds. That's how is it. This is 45 seconds. But if it happened here, let me clear everything. Oh, I can clear. So if I clear it, it happened here. What's the time then? Again, 20, 33, and how many seconds? Yeah, as
3 seconds.
as 48 seconds. Saad answered you. Saad al-Ismaili. Why 48? Because this is 45 and I'm continuing. Plus 3. Yeah, 45 plus 3. So if it happened somewhere instead of here, it happened. This is how usually all the records are. If it's happened, let's say, let me use a different color, blue color. It happened here. So this is 48, 51, 51, 54. This is 54, 57, 60. It means in here exactly at that time is 2034. That's 2034. And how many extra seconds? 20. No. 60. Yes. يعني الدقيقة 60 seconds. 34. Then 03. So here exactly is that much. Why? Because here it's 60. Sorry, here is 60. 20. 33. It went 60, so it goes 1 minute. Yes, 1 minute extra. 1 minute, 3 seconds. The total from here, add how much? As Reem said, 1 minute, 3 seconds. From here to here. So you can do something, calculate how many seconds, total seconds are, just add them. If they are 60, it's 1 minute. Yani if the total seconds were 125, it means 2 minutes and 5 seconds. So if you start calculating from here. But you are given another time span here. This just to help you, because from here to here, 3 minutes. From this point up to this point, 3 minutes pass. So start calculating 3 minutes. How many seconds? Up to here, 45 seconds. This is, you continue from here, then this is 36 minutes and 48, 51, 54. This is 57. And this is the start of P. It's not 60, it's more than 60. Let's say it's 58. So it's 20, 36, and 58. That's the start of P wave. What is the start of, where is the start of P wave then? Sorry, S wave. Where is the start of S wave? Where do you think the S wave is? So this was the first one, 53. And this is, let's take this an example. Try to get me the 56, 55, 59 for first observatory, which is San Andreas, the first one. So it's, this is, let me again make a drawing. So if I go back to this slide, I see, I already give you an example for these two. So it's more than that. By how much? By almost 4 or 5 seconds. 35.5. And this is 59. 53.5, 59. So it's almost 5 seconds extra, which is this one here. So here is the P. This is the P. And here you can say is 3. Here you can say is the S wave, where the change, there is a change. P then S, P then S, P then S. Where is the Rayleigh waves, surface waves? They arrive later on, later, sometime later. But I'm not taking them into.
There is a question in chat.
Huh?
A question in chat.
There is a question. Why did we start counting from that line above red line? Why did we start counting from that line above the red line? I couldn't understand your question. If someone understand what she's saying, can you say it in Arabic? Why we start, did we start counting from the first, that line? Which line you mean? No, you can count from this line. You can actually count from this line, sorry. So you can count if you like from this line. It's fine. So how they were made? Because this observatory is always recording. At every time they record, they keep recording. And at the time when a shaking happens, whenever there is an excitation with the ground, it's gonna be recorded here at that specific time of the day. So they go like that. And why they made them not very continuous, just for visualization. Yani it's gonna be easy to visualize instead of having very long papers. They make them like that.
دكتور يعني الحين احنا نشوف الخط الأحمر ونستعين به عشان نحدد الوقت في بداية يعني
لا
الموجة.
ما الخط ما not just the red line but all the lines. يعني this is the black line is a continuation.
أيوة
Yeah, but the red line
بس نستخدم على
whenever.
المعرف عشان نعرف
Yes,
الوقت.
yes, that's true. So you plot them here. You bring them, put them here, and calculate the difference in time. So what's the difference in time? You get it here. Once you do for Stanford, for Leak, for Berkeley stations, get the time here and see how much the difference in terms of second between P and S. Once you get this difference, use this chart. Use this chart. So try to get how much is the difference in time. Let me draw it. Use this one. So try to get how much the difference in time, and you need then to draw a line like that. Okay, I think that's the difference in time. Or use exactly this line. You see, this is the line, S minus P wave time. That's the line. This is the one. Get the time difference. That's the time difference. Record it. Get it somewhere here. For example, that's the one. And try to get the distance to the earthquake epicenter. Bring it down. And this is then what you supposed to give in the last column, which is where? Which is here. So 5.5. Let's see where is 5.5. This is the 5.5. 5.5. I go here and try to get the distance to the earthquake. San Andreas Observatory, which is given you here. Do the same for the rest. So once you get the distance for all of them, there are 4, come back to here, get your distance, use a fragile protractor, what they name it, protractor, bring it here, try to find, for example, 40 meters is that much. This distance from here to here is 40 meters. So draw a circle using this scale. And whatever for the other Lick Observatory, Stanford Observatory, draw the same. This is the Berkeley Observatory, draw circles. And locate where the earthquake is. Locate the earthquake.
دكتور لازم نطبع الأوراق هذا ولا كيف؟ ولا تسوي في الكمبيوتر؟
If you do something with computer, you don't need to print it. I can tell you how to use computer, but if you can use something with computer, you can do it easily without much problems. And I think there are some programs which can help, online programs. If not, then print it, scan it, and attach it back. And so this is the question. In here it asks, what is P wave arrival time at Santa Cruz? That's Santa Cruz. So what you do, you go to the map, try to find where is Santa Cruz. Where is Santa Cruz? That's the Santa Cruz. This is Santa Cruz. You try to measure what is the distance from Santa Cruz to the epicenter. And wherever you find the point of the earthquake, that's your epicenter. Someone is saying Adobe Illustrator. I use something else. I think it does the same. Adobe Illustrator is not free. Forgot the name. Let me search for it. Maybe I can help you with it. Inkscape. I use Inkscape. So this is Inkscape. I use Inkscape. It's free and similar to Adobe Illustrator. So what you do, you get the distance from Santa Cruz to the point where the earthquake is, the location of the earthquake, once you define it from the previous question. You get the distance supposed to be in kilometer, and if you get it somewhere, for example, maybe let's assume that your earthquake is somewhere here, just an assumption. And this is the distance. How much this distance is in kilometer using this scale? How much is it in kilometer? Once you find it, you come back to this graph. You calculate the distance. How much is it? Whatever is it? Then what you do? Again, you draw a line going up to the P wave and getting the time of the P wave. Whatever is it? So that's the distance to Santa Cruz. You go up to the P wave line and get the time of the P wave. And this is exactly this question. What is the P wave arrival time at Santa Cruz? And what's the origin time of this earthquake? That's the last question. For the origin time, this is the graph you need to use. You cannot use this one. This is just an example. You need to put it or use Excel. I think all of you have Excel. So in Excel, you make two different columns. One of the columns for 4 observatories, you put arrival time of P. And the other one is the difference between S and P, which are the one you already got here. Arrival time of P and the difference. So this is the arrival of time of P. And this is the difference in time between S and P. At the location where this line intersects the x-axis, that's the origin time. What's the origin time? At the time where this intersection is. So you got already your hour, minute, then seconds. 31 seconds, 30, and so on. Because the variation is very small from one place to another place. And the variation in seconds, it's not in minutes. Actually, between all of these observatories, and the variation for P from here to here is not more than 1 minute. And they are still within the last black line. You see the last black line. The last black line, one whole black line, one continuous black line is just 45 seconds. From here up to here is 45 seconds. But they're all within the black line. So you plot them here in the last graph. You make the graph in Excel. At this point, In Excel, how you draw this line? How you can draw this line? This is the line. In Excel, you just go here and there is an option saying best fit line. Draw a line. Draw a best fit line. And do projection, and you can project the line. And you will find at which point it's cutting through the x-axis. And that's the origin time. Why is that? As I said, at what time the P and S are the same? At the origin. At the origin, at the location where the earthquake happened, there is no difference between P and S. They arrived at the same time at the origin. So this is zero origin. The zero difference in between S and P. This will give you the origin time. Origin time. You will get the origin time from P wave, arrival of the P wave. Time, arrival time of P wave. So these are the questions for the first part. These are related to what? Earthquake location. I will be available. There is another guy, I will send his name to you. Contact him. His name is Saeed Al Farsi, sorry. He's a graduate student, so you can get help from him. Then we move to the second part. Second part is simply about focal mechanism. Yani first thing we know where the earthquake happened, but we need to know the earthquake happened because there was a fault. Can we tell what is the type of fault? Yes. From earthquake data, you can tell what type of fault was initiated. Whether it's normal, reverse, or even strike slip. And how it can be done? The forces, this is a linear force. You don't need to understand them in detail. This is a linear force. This is a coupled force coupled. This is also a coupled force. And some of the forces are double coupled. Have you heard of torque? Do you know torque? This is torque. 2 times force over the distance of the arm. Have you heard of clutch? Gear in cars. Do you know what's gear in a car? Maybe you are too young, you haven't heard of manual gear. Long time ago, the cars were all manuals. I think you know them. You're not too old.
Yes, doctor, we know.
Yeah. So the torque is very necessary to move the thing. And the torque is always something rotating. You rotate it. If you try to open for example, a can, trying to open a can of Pepsi or something, you need to have a force and you need to have an arm. If you have a long arm to pushing it, you can easily increase the torque. Yes, and gear is a torque. Your car will not move unless it has a torque. It has a high initial torque. So the cars usually, how they can tell it's strong car, good car or not. So they need to calculate 2 things. One of them is the speed. The other thing is first thing is what's the maximum speed? The other thing is torque, car torque, Newton meter or something they calculated. So usually trucks, big trucks, they have low speed, but they have high torque because they are so big, you need to have a high torque. torque. So when you start moving the tires, the car tires, initially the car is at stop. You need to move it. You need a high torque. The gear of the car gear is simply an arm. To have a high torque, you change the arm. There are some arms there, yani. You get a high torque to let the car move. Once the car is moving, you don't need high torque. The car is already in move. You need smaller torques. You don't need to exert force. Car does not need to exert force then to move itself, to start moving. It's already in move, because the higher the torque, the more fluid or more oil it consumes. Most of the earthquakes, there is no torque involved in these forces, which are generated by earthquake. We call them double couple force. They are exerting in different directions. So the energy generated from the earthquake is so huge, is so devastating, but still the earth is not rotating or changing its direction, rotation direction. Will start moving the same rotation direction without being affected. Earthquakes are all double coupled. There is no torque with the earthquakes. So what's the type of energy usually associated with an earthquake? Let's assume there is some electrode planted to the ground. I'm having a hammer, and I start hitting this electrode or peg with the hammer. What is the type of force you will find in this direction? What is the type of force you will find? You'll find something pushed you. If I'm here, I'll find someone pushed me away, push force. But since the earth is one continuous shape, I pushed from here. What happens here? This will be moving in this direction. This moves. This feels that someone pulled it. Someone pulled it from this direction, but this one feels that someone pushed it. That was the boundary. I hit in this direction. This will feel what? Someone pushed it. But anybody here, because the earth is one, we are one person. This one feels that someone pushed it. Is it clear?
No, again, Doctor.
Again. Okay. I'm not sure. I don't have something good to explain with. Anyway, I will do it again. This is something boundary. This is a boundary. And let's assume this thing is attached to me. It's totally attached to me. I'm two parts, but I'm attached to each other. There is something separating me. This is my hand. But it cannot be removed from me. So someone hit me here. My half will feel that this half will feel someone pushed it. Someone pushed it away, pushed it to this direction. But this part of my body is attached to the first part. What this part will feel? It feels that someone pulled it. Someone pulled it. But this one feels someone pushed it. That's the same phenomenon with the earthquakes. So the earthquake, if I hammer, this part the north part, the north direction, will feel that there is a push. I'm hitting the ground. The south part will feel someone pulling it. The push, we name it compression. The push, we feel it compression, while the southern part or the pull will feel what? Dilatation. I feel some part compression, the other part of the earth is feeling dilatation. So if there is a geophone here, the earth, the energy is arriving, the first energy is a hit in the north part. Is the hit is going up because I hit it. Whereas the other part of the earth, I pushed it, I pulled it, so it feels someone bringing it down, something bringing it down. This is called dilatation. This is compression, this is dilatation. The energy, the first energy, it goes away, but it's coming down. It pushed it, but here there was a pull. This is the pattern, radiation patterns, we call them. So whenever there is, let's assume that this is, let's make it somewhere. Yeah, that's fine. Let's assume that this is, let me draw it here. Let's assume this is my fault plane. What type of fault if the displacement are as shown? This is moving up, this is moving down. What type of fault is this then? Who can tell? There is a fault plane. One area of the fault is moving this direction, the other one is moving. No, there is no up, down. It's, you are seeing from the top. I'm seeing right now from top because this is north, south, transform. Yes, strike slip. Strike slip dynamite. So I'm seeing from top. I'm watching this fault from the top. North, south, east, west. This side is going down, this side going up. So if you have any geophone here, let's assume there is a geophone. What this geophone, the one here, what it feels? Will it feel a push or a pull? Will it feel a push or a pull? A pull, sorry. The geophone here. Perfect, Basma. That's what it feels. It feels there is a push. What about this geophone here? Two. What it feels? Feel the pull. Here you'll feel that there is a pull. Someone pulled me because this is, it's moving up. It feels that someone is pulling it. The first motion is a trough. Here the first motion is a peak. So the trace moves like that. Up. And where? In here. Whereas for this one, it's down trough. The first motion is down. Whereas here, P wave, that's the P wave. This is the start. Feels a peak. Whereas here, I feel a trough. Similarly, what I gonna feel here at 3? What is the type? Is it a peak or trough here? If there is a geophone here, what's the sense of motion of P? Not peak, it's peak. So Basma, peak. Yes, it's a peak. You will feel a peak here, whereas you feel a trough. It's all demonstrated here. This is the radiation pattern. All of this area will feel a peak. All of this but here they will feel a trough, and so on. So this type of pattern tells you that this is strike slip fault. But what you need a lot of stations. Yani stations here, here, many stations. Otherwise you cannot tell. So this is the compression, this is dilatation. This is a dilatation again, and this is a compression. So for strike slip fault, what do you think? Where is the fault plane? That's the fault plane. Am I right? This is the fault plane. This line is the original fault plane. But if you have this pattern, sorry, if you have just this pattern, yani plus here, plus here, and negative here, how many possible planes are there? How many planes, fault planes are there? Two. يعني why two? It's double couple. Two, not four. Malik, four, two. That's true. Because it can be this way, going up. This is the actual one because I'm just demonstrating to you. But it can also be this one. How I can make it bigger? Customize. Thickness. And I'm not sure. So this goes this direction. This goes this direction. You will get the same pattern and the same shape. Here I get compression, dilatation for the blue one. Here I get dilatation, compression. So I cannot tell easily which one is the real plane and which one is the auxiliary plane. Fault plane is this one. So what is fault plane? This is a rupture plane or fault plane. That's what we call fault plane. Let's make it very quick because I think you have studied this in geology 1. So if there are two plates against each other, or let me use these two things. So two, they move that way. Wait, you see? One of them moved this, the lower one moved up. Let me see how it looks like because I want to see myself then. If anything is not clear. It's moved this way. It's oblique fault. It's kind of oblique fault. This is a fault plane. So that, let's assume this is the north. The direction from the north to this plane is the strike. This is the dip angle. That's the dip angle. Dip angle, if I draw a line and from the plane to the horizontal, that's the dip angle. The strike or the slip is this angle, how this moved. Calculated from horizontal. Up from here, up to here. So this is the anatomy of a fault in general. I don't want to go to the details because this is not the topic of this course. But we need to draw this plane. Usually we draw it in a hemisphere, a total hemisphere. So this is how it looks like in total hemisphere. I have the strike from north calculated. I have the dip, which is 25. This is the real one. Oh, sorry, this is the real one. and this is the auxiliary, and the difference between them is 90 degree, or they all of them. I mean, if you add 25, let me draw it. So from here to here is 75. This is the, from here up, from north up to this direction is the real strike. Is the real strike of this one. And this is the fault plane. Doing it in this way is not easy. And using a 3D shape. We draw it in what we call lower hemisphere. Yani we cut the upper part, only use the lower part. So the lower part, for the lower part, I don't want to go to the details because you will not understand this thing unless you do them by hand. So don't care about these things too much. So this one here, this one is basically this thing. Whereas this one you see here, oh, this is still red. Customize. Just use this one. So this one you see here, fault plane. This is actually this one. Oh, I said it's 75, but it's not 75, it's 65. 65. So this is the strike. This is the strike of this one. And this is the strike of the both of them. Oh, sorry, this is the dip. They call this one azimuth. But you don't care about the azimuth. We care about the strike. The strike is 125. Both of them, they have the same strike. Both of these auxiliary and they have the same strike. And if they are perpendicular to each other, they have the same strike. This is where you calculate the strike, 125. But one of them having a different dip than the other. So this is how they look like. They name it beach ball. They name these things beach ball. Why they named them beach ball? Beach ball. In geophysics, they named them beach ball because they look like something similar to this. So the thing you are seeing here, it's called beach ball. And we call them skimmet net. So don't care about this one. I don't want to confuse you much more. But how they are drawn, yani, this is very important. This is what we care. But we'll not do it in this course. We need to just understand what are the types. For example, for strike slip fault, this is the type of beach ball you will get. For normal fault, this is the type of beach ball you get. Whereas the thrust fault will give you something similar to this. You will see that normal and thrust faults, in terms of shape, they are the same. The only difference is the dilatation or compression direction. The compression is in the middle for thrust, whereas it's in the where the dilatation is in the middle for the reverse faults. We explained why we get this shape for strike slip. Can anybody tell me why I'm getting this one? Or shall I explain it? Let me explain it so you understand at least why I'm getting such shape for a normal fault. So this is the normal fault. Let's assume I'm I'm seeing this one from above. I'm seeing this one from the above. Let's assume there is a geophone right here. And there is one here and one here. So from the direction of the arrow, I'm pushing this thing down, pushing this thing down. What I get here? A peak or trough? Can anybody tell me? I'm pushing this thing down. What I get in the middle? In the middle, what I get? So I'm pushing this thing down. Let me draw it here. You see this thing? This is how normal fault is. So if my geophone here, what I get here? A trough. This moved down. There is a trough. What I get somewhere here? All of this moved down. The energy is moving down. All of this block here is moving down. But here in this part, I pushed it down. So it moves. The first moving is down, moving like that, making a compression. Here is compression, compression, compression. So the geophone here, which is this one, by the way, will get a compression. The energy radiates from down up. As we know, the energy, the rays will move and come back to the surface. So this one will get a compression. This one here, the geophone here, which is this one, anything here, will get also a compression. This is very simple because I'm pushing up. Here I get a compression. The only place I get a trough is here. Is where in the middle, on top of the fault plane. The thrust fault is the reverse. So the reverse thing happen. The reverse thing happen. These things, we name them beach balls. And they can tell you exactly what is the type of fault generated by an earthquake. So this is how they draw them. Whenever there is an earthquake, they can tell the earthquake. And for example, this is a thrusting fault. You see, this is a thrust. Thrust, usually in geology, they draw them like that. Any line and some arrows like that. You see, this is how the thrust is usually shown in a map, in geologic map. And all of these, you see these beach balls, they look like what? Here we go, our previous slide. They look like this one. It's a thrust. And they are all from the same fault. This earthquake happened here, 7.5 magnitude. This is, I'm not sure how much is it. This is 6.9 and so on. They're all from the same fault, and I'm having a thrust fault. Here is a normal. This is a normal. This is what you know. Do you know what is this? The oceanic ridge. This is mid-oceanic ridge. All of the type of faults here are normal faults. So those are normal faults. You see the trough is in the middle. Normal fault. It's having a beach ball similar to the normal fault. So these are all normal faults. This is another type. I have African plate, and here I'm having a strike slip. It's all strike slip. which is similar to the one you see here. So how we can use these things for our lab? So our lab is what you see here. What do you think the mechanism for this? What type of mechanism is this? Is it a normal, a reverse, or strike slip? Yeah. Can you give the direction, strike direction, and the approximate dip? Rough numbers. The strike is this value. Let me draw it. As I said, this is north. The strike is from here to here. This is how much you think is 15 probably. And what's the dip? I divide it. So from here to up to here is 90. How much is the mid? From here, measure from here to here. How much is this one? Is probably 45. Which one is the normal, sorry, which one is the actual fault plane and which one is the auxiliary? I cannot tell. And one of these is actual fault plane. The other one is the auxiliary. This is a normal fault. This is the strike. That's the strike, and this is the dip angle. This is the dip angle, which is 45. Calculate from here up to here. Do the same for the rest. So this is a thrust fault or a reverse fault. What's the strike direction? Strike direction measure from north up to here. It's almost like close to 100. That's the strike direction. And it has two different dips. This is one dip. This is another dip. The dip, you measure it from here up to here. So if I draw it, I will show it to you. So what's the amount of dip from here to here? It's almost like 40 or 30. And how much is amount of dip from here to here? Is close to 80. It is close to 40. What is the strike approximate dip of the faults? Two faults. Why two faults? One is the auxiliary and the other one is the real. And finally, what is this one? This is basically strike slip. Strike slip, they do not have a dip direction, or there is no deep direction, but there is a strike direction from north to here is the strike. And finally, you got a lot of these things. Yani someone did these things. These are peaks. You see, many stations, they are peaks. Those are troughs. So what's your task? Or simply here, you are requested right now to draw these planes, fault planes. How you draw them? Draw a line separating between black and white. Draw a line separating between black and white. The simplest way is draw this one and draw the other one. So what type of fault is this? What type of fault is this, you think? If I strike stick. So these are black, push. These are push. These are dilatations. This is how simple is it. This can all be done through earthquake, and they do it quite often. and it's really done during earthquake. So I think that's it. There is no more questions. I almost answered some of them. So your part is just to go answer both of these. Maybe the location is quite tedious, more tedious job than this one, than focal mechanism. This is what we call focal mechanism. Whereas the other first one is locating the earthquake. And I'm available for you in case you have any question. Do it, convert your Word files into PDF, and finally come to the module and upload them as PDF. The link is already there. So we have almost like 20 minutes or 25 minutes, but since I was explaining most of the time, I haven't given you a chance to do anything. I'm happy to receive any questions you probably have. Do you have any questions, guys? Otherwise, you can
دكتور
submit the...
آخر لاب ثاني دكتور.
ها؟
المطلوب من لاب ثاني.
آخر سؤال؟
لا أيوة، اللاب ثاني سؤال.
أيوة.
الأسئلة.
أيوة.
وش المطلوب من هنا فيه تحديد وش؟ أنا طلعت
هني
شوية.
Yeah, below are some first arrival plotted, يعني first arrival. There are a lot of stations. You see, these are all stations. Some of them, they record the peak. First motion is a peak. The others, they record first motion as a trough. So your task is to draw the fault planes. There are two faults. One is the real fault plane. The other one usually is the auxiliary. Draw them. I cannot tell directly from these beach balls which one is the real one and which one is the auxiliary. We need to bring some field observations, other field observations, or geology. And in San Andreas, we know that the plates are moving apart, and usually there occur what type of faults are there in rifting basins. It's a rift. Two things are moving apart. It's a rift. Normal
أنا
faults.
دكتور جواب.
So the answer is draw these things, draw these lines, determine what's the type of fault.
No, Doctor, I mean first question, not this question.
First one? This
Yes.
one you mean?
Yes.
Determine what is the mechanism here. Fault mechanism. There are three types of fault mechanism we talked about. Reverse, normal, and strike slip. What do you think is this? What do you think is this?
Normal.
Normal. That's a normal. The other part is asking what's the strike? The strike is this one. From here up to this point. What is this angle? How much is this angle, you think? Don't need to give it very accurate, but an estimation. This is the strike. The last question is asking how much is the dip? The two planes, one is this one, and the other one is this one. The plane, I start measuring it from here. Here up to the middle, where I can cut it from the strike. So total from here up to this point is 90. So how much is this from here to here? How much you think is it? No? From here, measuring from here up to here is 90. A circle is one half of circle. This is half hemisphere. Lower hemisphere is 180. So this is 90. So this is how much is 45. The dip angle. So plane has a dip angle of 0. up to 90. That's a vertical fault. If there is a vertical fault, it will be drawn like a straight line. If it's horizontal fault in the lower hemisphere, it will be drawn on like that. This is a horizontal fault. It's 45-degree fault. It will be drawn like what you see here. This is 45. I think you have studied this in structural geology. This is just a reminder. But yeah, I made it simple for you how to calculate the dip angle and the strike. This is the strike. Strike can be this one or the other one. From here to here. Yani. Whatever you get. If this is like 20, what is the other strike? 20 plus 180. This is here, yani. If you go back, the strike can be here, this to here, or from here to other line, other part. From north to the other part, or north to first part. Usually we consider only the first, the shortest one. That's the strike. This is the dip. That's the dip of the fault, which you can bring it from here. That's the dip from here to here. That's the dip. Is that clear?
Yes, دكتور.
You do the same for this one. Mariam, are you petroleum geologist or a geologist? Huh? Or a geophysicist? Petroleum. Yeah, it might be difficult because you haven't studied structural geologist, but make it simple. For example, the first one I already answered. Let's assume you want to get, first of all, what is the fault type or what they call it mechanism in here? What's the mechanism? It's a reverse fault. This is a thrust. They call it thrust too, or reverse fault. In Oman, in North Oman, we have a lot of thrust. Why? Because of ophiolite. Ophiolite is creating, it's coming to the Oman. Ophiolite is oceanic crust. Oceanic crust.
دكتور, the
came to the
thrust
Oman.
is if it is less than 30 angle.
Yeah, that's true. But they are reverse faults. Am I right? So what is the strike? If this is the north, this is the north. Where you see this dot, this is the north. What is the strike? You start measuring from here up to here. That's the strike. How much is this from here to here? It's close to 95, 100. That's the strike. And what's the dip? If I draw a line in the from this within the strike, a line, straight line, measuring from north, from here, from the middle of this one, up to this line, this is 90 degrees. So how much is this one? Starting from zero, how much is this one, you think? How much? Give me a rough number, Mariam. Give me a rough number. It's close to 40. Am I right? And how much is this one from here to here? 0 and so on up to here. It's almost 80 or 85. They call them also stereographic projections. Oh, no, you will get me confused later on. So we don't need to confuse you much more. You have two, one of them is, this line is, one of them is the real plane, I'm not sure which one is the real plane. The other one is the auxiliary plane. The other one is the auxiliary. Yes, you can. So any more questions? Any more questions? If you have anything related to this lab, please ask me. The materials are here. Download them, then answer among yourself. You can get help from each other. You can ask in Google Hangouts. I hope you are part you are there in Google Hangout. If not, please ask me. Are you there in Google Hangout or not? Send me a message. So I let you in. If you don't
Okay,
have
Doctor.
if you don't have anything to ask, I will